Okay, well, thank you. It's certainly a pleasure here, be in Florence and at this institute. Not everyone here was here last week. We got to go up and see Galileo's house. It's really an incredibly important place, and is it for most of the time. So I'd like to tell you about a gauge choice for infrared singularities, and I'm describing work with Zoltan Naic. And it will be published soon, but so what I'm talking about is interpolating gauge. And that was invented by Dust in 1987, and then reinvented by Belleau and Zwanziger in 1999. Our interest, Zoltan and mine, is in improving the description of soft and collinear singularities in QCD. It might be useful, this gauge, for defining subtractions, for instance, in higher order calculations, where you have to remove the singularities from your calculation. So a lot of people here might be interested in it for that reason, and that's why I've suggested it maybe it'd be good to give a talk about it. Zoltan and my interest is in defining the splitting functions for a next to leading order parton shower, which is rather a big and complicated job, and we want to have a check which gauge would be best to do that in. And we found this one in the literature. What it does is it interpolates between Feynman gauge or Lorentz gauge and Coulomb gauge. And Dust and Belleau and Zwanziger were interested in this interpolating gauge because they wanted to better define what Coulomb gauge is. As you may know, if you just naively start to calculate in Coulomb gauge and you have enough loops, things go bad. So this way they could have a good definition of it. Well, our goal is not that. I don't really care about Coulomb gauge. So we've adopted a different notation from the original authors, and we emphasize different features of the gauge. And in this paper, we explore some technical issues in a certain amount of depth, but I'm not going to go into too much technical details. What I'd really like to tell you about is why this gauge might be interesting. If you find it's interesting, or maybe you remember 5 years from now that it's, oh, well, there's this neat gauge invented by Dust and Zwanziger and Belleau, then you could just look this up. And the important thing is to remember why it might be useful. So first of all, why not just use Feynman gauge? It's incredibly simple. But consider a virtual gluon. So here's my virtual gluon, and it's connecting to an outgoing line on some kind of graph, an outgoing on-shell massless line. And this just designates a completely complicated graph with other external lines. So my gluon is carrying momentum Q, let's say, into that vertex, and it connects to a line with momentum PL. So this line here is momentum P minus Q. And when Q gets to be collinear with PL, it's X some scalar times PL, then there's a singularity in the loop integral. And that singularity is enough to give a logarithmic divergence. So that's not so bad, but that happens no matter where inside of here connects. Right in the middle of some hugely complicated graph onto an off-shell line that's off-shell by hundreds of GeV, say. Nevertheless, there's a collinear singularity. The gluon, when it's connecting here, has unphysical polarization. That is, if J mu denotes the current up there, then J mu times the propagator for the gluon is proportional to Q nu. So that physical gluon has transverse polarization. This has polarization along the direction of its momentum. And that helps because you can use word identities based on this Q nu factor to get rid of these gluons, and you just connect it everywhere in the graph and it'll come out everywhere except where you don't connect it, which is this external line. So that works just fine, and that's the way people mostly do it at least at first order. However, if there's more than one collinear direction, and there's, well, there are always more than one collinear directions, but if there's more than one of these gluons, then you start to be in trouble, because now you can have multiple gluons that are of different collinear singularities and they can interact with each other, and it gets to be rather complicated. Sperman have investigated this and figured out how to use the word identities to straighten this stuff out, but it's sort of complicated. So we preferred not to do that. So after investigating this gauge, our opinion was that, wow, maybe it'd be better if that didn't occur. Just no graphs of those unphysical singularities. And we looked around, tried to figure out how to do this, and there in the literature was this nice gauge. So this is a not covariant gauge like Coulomb gauge. So it has to have a vector n that points in some direction, and it's a time-like vector. So you can best think of this in the reference frame in which n just points along the time axis. And then we define a tensor h mu nu whose components in that reference frame are just -1, -1, -1 on the space directions, and 1 over v squared, where v is a parameter, 1 over v squared in the time direction. And then for any vector q, we define q tilde as h mu nu q nu. Okay, so that way the components of q tilde are q naught over v squared and then vector q. Okay, now we can define what the gauge is. We use a gauge fixing convention or condition d tilde mu a mu minus some omega that you're integrating over is 0. For one of the covariant gauges, it's d mu a mu minus the same thing that you're integrating over equals 0. So what you've done is you've taken d mu a mu, that's d mu and g mu nu a nu, and you've changed it to d tilde mu a mu, what's d mu h mu nu a nu. So you've stuck a different metric tensor into that relation. And then you work out what is the gauge fixing Lagrangian from that condition. And it's d tilde mu a mu squared, and then times the normalizing factor v squared over 2c. C and v and the vector n are then gauge parameters. It's best to choose c equal 1. That corresponds to starting from Feynman gauge, but c equals goes to 0, corresponds to Lorentz gauge to start with, and we'll see what v does. So here is the propagator, or gluon at tree level. 1 over q squared, and it's got a plus I epsilon or plus I 0 convention on it that makes it causal and allows you to do all kinds of integrals over Q, because when you come to one of these poles, you just go around the pole. Minus G mu nu, and then plus Q mu, Q tilde nu, and the other way around, divided by Q dot tilde. And minus over Q dot Q tilde. And then if C is not one, there's C minus 1 over V squared, Q mu Q nu over Q dot Q tilde squared. This one's not got that 1 over Q squared. Best to think of C equals 1, and then you just get rid of it. So that's what we usually would choose. But when you're doing renormalization, you have to allow for C to be a variable because it gets renormalized. Okay, so let me just tell you then about the complete gluon propagator. You can take the d mu nu, that's the tree level propagator, and divide it into two pieces, d transverse and dl. And d transverse is 1 over q squared plus I0 epsilon mu epsilon nu. Those are polarization vectors. There's two of them. You sum over the two choices. I'm taking things that are real and transverse to q. So epsilon dot n is 0 and epsilon dot q is 0. So this piece defines the propagation of inversely polarized gluons. So those are the guys you want, but there's this other DL. And remember, we had the complete gluon propagator, so DL is whatever's left over. And here's what the components of DL are in the right reference frame. Minus 1 over q dot q tilde. Space-time, 0I components are 0. And the IJ space-space components, 1 over v squared, 1 over q dot q tilde, and then qi, qj over q vector squared. So look at those denominators, q dot q tilde. So if you're integrating over q and you run into that pole, you just go around it in the right direction. And that's much better than an axial gauge where you have 1 over q0, say. With no I epsilon, you don't know what to do when you come to q0 equals 0. What is this q dot q tilde? It's q0 squared over v squared minus q vector squared. So the condition for on-shell propagation is that q naught equals plus or minus v, is the absolute value of q. That's in momentum space. Before you transform that and figure out where are the singularities of the space-time propagator, it's at position x, absolute value equals v times t. Now that's a cone. I drew a picture of the cone. Here is a light cone. That's where the singularity is in propagator for a transverse gluon. And then here is the other cone for the ones. And well, I just drew it, it's outside. In any reference frame, it would be outside of the light cone, but it's particularly simple in this reference frame. So what do I learn? In this vector n equals 0 frame, the L gluons propagate with a speed bigger than 1. And that has important consequences. So just to keep things simple, let me make C equals 1. That starts us off at Feynman gauge. And for V going to infinity, that whole gauge turns into Coulomb gauge. Well, which is the important part that's in the denominator, just turns into 1 over q vector squared with a minus sign. So that's the Fourier transform of the Coulomb force. And it propagates instantaneously. That always seemed a little strange. when you've learned quantum electrodynamics from, say, Bjorken and Bell, whoa, you wiggle a charge over here and instantaneously over there, that charge feels it. And that's what happens. That's the nature of Coulomb gauge. Here, we don't have that. Coulomb gauge is defined as a limit when V goes to infinity. So there's the L gluons propagate with some finite speed, but the speed isn't infinite. The authors from whom we got were wanting to investigate Coulomb gauge. So they wanted to take the limit V goes to infinity, then that'll define all the problems. You get rid of all the problems of Coulomb gauge, you just carefully take that limit. We don't care about Coulomb gauge. So what's important for us is that it's not finite. So we can take any V we like, and for instance, just take V equals 2. So that was a tree-level gluon propagator. Let me just say a couple words about the propagator, the full one. So the full gluon propagator base, well, it's the tree-level one plus the tree-level one times the self-energy of a gluon, which you have to calculate some graphs, times G. And you can just expand that formula out to get a whole series. This D, the tree level version, is a transverse one and a longitudinal one. So we just talked about that. And the transverse one has a numerator P transverse, that's epsilon mu, epsilon nu. And the longitudinal one has whatever is left over. And the transverse one is divided by P squared. And the longitudinal one is divided by P dot P tilde. And there's no 1 over P squared in the longitudinal one. So you can also just decompose the self-energy into transverse and longitudinal parts. And I have to say, how do you do that? So the transverse part is the same PT times a scalar, letters are just called a scalar pi. And the longitudinal part is something times P mu P nu, something else times N mu N nu, something else times P N and NP, but no G mu nu. The G mu nu is part of P transverse. And P transverse has the properties that, I should mention that D mu nu L has P mu P nu that is the same kind of decomposition. So P dot this tensor PT and N dot tensor PT are 0. Because the epsilons are perpendicular to Q and N. So those things all together give us D times pi, D transverse times L 0, and pi transverse times DL 0. So when I now put those conditions into the general expansion of the full propagator, I find that G is G transverse times plus GL, where G transverse is D transverse H transverse dot D transverse, et cetera, but all transverse things. And the L is DL plus DL, pi L, DL, and all the longitudinal things. So that just breaks the complete gluon propagator into 2 pieces, one for propagating transverse guys, one for propagating L guys. And the G transverse one, that's for the T gluon, has poles at P squared equals 0, but no poles at P dot P tilde equals 0. And the propagator for GL has poles at P dot P tilde equals 0 if you expand it out. So term by term, it has poles right there, but no poles at P squared equals 0. So it just completely is separated. Okay. So now, why is that maybe useful? The T gluons do not give any collinear singularities. That's the basic reason why it's useful. And that's because if Q gets to be parallel to PL, then the current here dot the numerator epsilons is 0, because then Q, this current is proportional to PL, but that's proportional to Q dot epsilon is 0. So that just cancels the collinear singularities. Except if this couples back to that same leg. And it's just because Q dot epsilon is 0. Okay, so that was a good thing. The L gluons also do not give collinear singularities. Why is that? It's because when Q is parallel to PL, this one gets to be on shell, it's PL squared. But then Q squared, which was contributing, 1 over Q squared was making a singularity, is now become 1 over Q dot Q tilde. And if Q is light like Q dot Q tilde is not 0. So this kills the collinear singularities in the L gluons also. So there are none of these collinear singularities except if you couple back to the same line. So our interpretation is this is just like a physical gauge. You're like Coulomb gauge or whatever, but you don't really need to go all the way to Coulomb gauge. These both have soft singularities. So if I have 2 external lines on shell going in different directions, and I exchange one of these transverse gluons between there, and I count up when Q goes to 0, what's it? All right. There should be some soft singularities from exchanging between different external lines. If you exchange an L gluon, also the same power counting gives a soft singularity. So it's just that the soft singularities don't have on top of them collinear singularities. Okay, and I can just mention some technical issues. Normalization works. Well, these authors claimed all orders it works, but we wanted to be sure by calculating. So there's a renormalization. It's a tensor for the field A because A is a 4-vector and it's not all covariant. So it's a tensor with mu nu components for renormalizing the gluon field. And it's just a constant for the quark field, a constant for the ghost field. There are ghosts in this. Constants for renormalizing the coupling, V parameter, and the C parameter. And we just calculated all of them at order alpha S. And that's a kind of a non-trivial check because there's more divergences in graphs than there are renormalization counter terms. And what we found is it all works. Okay, so that's a good thing. We just wanted to be sure that, well, if we actually did something with this, we didn't want to find out a couple months later that it doesn't work. So it seems to us to work. Also, BRST invariance shows that the S matrix between physical states, either incoming or outgoing, is independent of the parameters V, C, and N. And I have a slide for that. I'm going to just show you the slide. We can, if you want to know about it, we'll come back to that. But let me show you one more thing you can actually calculate with this. We wanted to make sure that, well, it's not hopeless. So we calculated the the gluon self-energy off shell, so it's not infrared singular, but it needs renormalization, so we have to subtract its ultraviolet poles, and it's pi mu nu. That's got a bunch of coefficients. It could be g mu nu, h mu nu, p mu p tilde mu, p tilde, etc. There's 1, 2, 3, 4, 5 different pieces of it, and we just calculated them all and made a graph versus for off shell, so p squared is not 0, and versus p dot p tilde over p squared, and we just used Feynman parameter representation and did the integrals. The integrals are then numerical; they're too complicated to calculate by hand. Or at least our computer didn't know what the answer was. But you just do those integrals numerically, and then we made a graph of it, and that all seems to work. So we have a conclusion. Our conclusion is, well, this might be useful for anything, in particular our project, where you want to control all of the collinear and soft singularities, and especially where you want to make sure that the collinear singularities don't occur just all over the place. They only occur in self-energy graphs. So we're busy now trying to use that, and I just suggest to you to just sort of remember that this is a gauge that actually exists in the literature, and you can use it if you like. Okay, thank you.
Thanks, Dave. I thought all the gauge invariant ingredients needed for building a parton shower at order alpha s squared were already known for a long time. I'm talking about things like the one loop collinear splitting kernel for 1 goes to 2, which was known since the 90s.
Yes,
or
well,
double soft emission, which is known at
there's
tree level.
lots of literature on this subject, but it's not so easy to put it together. And
why is it hard?
Is it hard? It's been 40 years since parton showers were invented.
Yeah.
There is, to this date, no next leading order parton shower.
What about the work of Stefan Husche and company? Have they been, but I don't think the issues in putting it together have anything to do with the behavior of the matrix elements. I think they just have to do with bookkeeping. I'm not saying it's an easy problem, but I don't think it has to do with gauge dependence. I think all the matrix elements, ingredients in every corner of phase space that you need, their behavior was worked out a long time ago, like triple collinear limits for,
Yes.
So why do we need this gauge? I don't get it.
Because we wanted to have a formulation in which you could take a Feynman graph and turn it sort of automatically into a piece of the next to leading order parton splitting.
Do you think you're going to get a different result from those previous results for the building blocks?
We found it was rather difficult to use all those previous results.
Why?
Why? Because they're complicated and you have to pop things around.
They're complicated, but they're gauge invariant, so you're going to get the same complicated results when you finish your calculation.
Yes, but we can get it in an automated way. So nobody has done this for 40 years. It has nothing to do. It has to do with bookkeeping. Well, nobody has done the bookkeeping.
Can I comment on this? Yes, I agree. So at alpha s square level, all these double soft, triple collinear, and all these things, limits are known for a while, at least in the last 20 years, I would say. So just like in a next to leading order subtraction scheme, you have to put this together to cover the whole phase space and avoid double counting on certain. So that's already a major task. And just to have at least the first next to leading order calculation based on this subtraction took. Right. Let come to this point. So when you do an NNLO calculation at fixed order level, so you have to do it at cross section level. So let's make it matrix element square level. So okay, you cooked out a subtraction. Maybe you missed you introduced a spurious pole. So that was always a problem in this subtraction scheme. So you could adjust a little bit doing a counter term. So you did this back and forth. But in Parton shower, we don't have that luxury. So we have to define this. So basically the singular structure, we have to factorize out the singular structure at the density operator level, at really amplitude level, not matrix element square level. So that's already a kind of restriction. And we have to, yeah, but putting together, you know, all these different regions, it's kind of tough. And then we have to take care about the momentum mapping, plus this kind of UV cutoff, when we introduce the shower evolution. So it's a more complicated task than just to do a next to next. Yeah, so that's what we wanted to avoid. That's what we wanted to avoid, just to, you know, try to sew them together to do all this stitching work, you know, between the different regions. What we wanted that if you draw a Feynman graph, you basically get the singularity structure in a factorized form. And if you use Feynman gauge, so because of all this collinear effect, and it pollutes the, you know, the graphs. You cannot do this factorization graph by graph basis.
Sure, it's already been.
Not graph by graph though, so
Not my graph.
doesn't work too.
Because that's simple and we have full control and we don't have problem with spurious poles when you try to put together the different region. And then another thing, we wanted a method what you can carry on for higher and higher order. So my purpose, okay, so the practical purpose. Yeah. Yeah, you can. Well, I'm not sure the light like axial gauge is practical if you go beyond the first order. So now you have more problem with the propagators, the gauge propagators.
Yeah, issues were not a problem. But still, they don't appear downstream. You have to organize things in a smart way, like using unitary, but it's not a problem.
So can I finish just about the gauge? So if I look at the propagator, so the gauge propagator, what you introduce with the axial gauge, even with the prescription, the line-blind Mandelstam prescription, so you need two vectors, n and n star. We need one, and in the denominator we have a quadratic form, which is much simpler. What you get. So we find it's less technicality, less technical problem with this gauge fixing than the.
If you can't do your integrals, you can bubble where you can.
Well,
we don't really care about having numerical integrals.
Sure.
In any case, in a Parton shower, all the integrals are done numerically.
So just
Let's talk about how.
Yes.
But I find it's very simple. If you draw a graph, you know how to get the singularity structure. It's so basically what we need. If you have M hard line, you dress up the M hard line with virtual and real emissions at a certain level, and that's it. You don't have to use word identity, nothing. Exactly, it's not process by process. This is completely mechanical, and it's a factorized form. So that's the point. Right. Yeah. So it's completely basically automatic, and the idea is to show that this whole procedure is kind of mechanically works beyond even the second order. I mean, the second order would be the practical. Sorry?
Are you going to check if you agree?
Sure. We would like to show that all the singularity structure. We are working on that.
Yeah. Simon, would you like to comment?
I mean, basically two comments. Right? So I think, Lance, you're right, it's about organizing the phase space, right? But what we're really interested in is, I mean, both Sultan and Dave, but also my collaborators and me, how you systematically distribute soft in between different collinear limits and so on. And this is still the big unknown. Also, Stefan has not achieved to fully solve this yet, right? Not even in smaller building blocks. So, and it ties very much in with the structure, how you build an iterative shower algorithm, because you need to build that thing on the level of amplitude times conjugate amplitude, not in the sense of a cut diagram, because then you look at just one emission of a hard process. But we really want to iterate this. We want to understand how the iterative structures simplify into an algorithm which you can then implement in a more probabilistic way. So this is it's really a different kind of approach of building the thing in a systematic way. And there you need to understand how that bookkeeping works and how you factor this structure beyond just say, okay, I look at this limit and then I get this, and I look at the other limit and then I get this. So we need to know how that works on the amplitude level. And try and no, I agree with you. I agree with you. I agree with your statement that these things are known to the extent that you know them in the strict limit. But what we're looking for is an interpolating formula, and this is no. I want to combine them across different limits. Yeah. Yes. Yeah. And then we see, for example, that this is highly sensitive to the way how you parameterize the kinematics. And this is something which links ultimately also to the question of logarithmic accuracy of Parton showers. Because you see that splitting kernels come out different in this interpolating formula, depending on how you set up the mapping and how you distribute recoils. And this is quite an important thing. This is why we're after. But on the other hand, I mean, no, that was comment number one, okay? Comment number two is basically that, sorry, it's a nice work. It's really nice work what you're doing. But once you have organized your phase space, you can stick to the axial gauge. It really does, to the light cone gauge. It really does everything you need. I can't see what the problem is with the Mandelstam Librand prescription, because that just works, right? The only thing you need to make sure is that your pole doesn't jump across the contour which you recrotate, but it jumps to the other place where it doesn't interfere with the recrotation. That's all. This is. If you do the integral, yes, but if you look at, right, that's the other thing which comes to Parton showers, because what we want to do ultimately is that we organize the integrals in cuts and rather look at the integrants, which we do by a Monte Carlo in the end in such a Parton shower algorithm. So there's a lot of work, and I think it's important to have different aspects here. Yeah, but that were my two comments.
Just comment on light cone gauge. I mean, maybe that works, but if you have hadron to jets or whatever, or Z bosons, there's two incoming directions. There's two light cone directions, and we thought it's best to have just one vector that's pointing in a time-like direction in the center of mass. Otherwise, you just have problems with that, having two light-like directions. But it's a choice, and maybe some other choice would be better. I don't know.
Okay. You want to comment directly?
So probably she could comment on this, even the Mandelstam Librand choice. So even at two loop level, she had quite a lot of problem to deal with this. Could be, I don't know the details, but
So like, here's a simple example. You have a triangle. You have a triangle with one off-shell leg, which is the off-shell gluon that's splitting into two on-shell gluons. You do it in light cone gauge. You have to use the Mandelstam-Librand prescription when the axial gauge denominator is on the leg that is downstream the furthest from the vertex, the one that goes across. However, that one shouldn't be there in the final expression because you can perform a unitarity cut at this point, and everything on this side is gauge invariant, and so it can't be there. And when you organize the diagrams, it vanishes. The only place you need that light cone denominator is down here, but you can show those integrals are perfectly well regulated in dimensional regularization. You don't need the Mandelstam-Librand. And we did this at 2 loops too, for the 2 loop, 1 goes to 2 splittings. Now I can't say that we know everything about the higher point things you need for soft, because I think you're going to need, you know, 1 soft emission at order alpha S and 1 soft loop in the alpha S squared. I didn't really look at that one.
we really wanted to organize things. So just to sum up certain set of graphs to get some cancellation. So what we really wanted, have a graph, and if you have singularities in that graph, it appears always in factorized form.
Well, we proved that the S matrix is gauge
Yeah.
invariant, so we can use whatever gauge we want.
A question maybe a little bit out of this one. So you mentioned ghosts, but you didn't discuss them that much. But as far as I can tell, you would have tachyonic ghosts, right? I mean, they propagate, but with
Yes, the
speed.
ghosts have 1 over q dot q tilde in their
And
denominator, so they're
does
tachyonic.
that not give problems with causality? Is that
I don't think so, but you just put them in. They're in virtual graphs, so ghosts don't go to the final state. And so you do the integrals. I don't think anything goes wrong, but if something does, we'll find out about it.
I was just quickly going to say you totally need tachyonic ghosts because you have tachyonic gluons that you need to cancel. So
It's just one comment and a question. So come back to the gauge dependence issue. So the first thing that we should declare is what are we after? Are we after a matrix element square Parton shower? That is what. In that case, let me finish then. In that case, as Lance and Simon said already several times, the problem is not really defining those blocks that you're iterating. Those are well known and they are gauge invariant. Is mainly covering the phase space and subtracting the divergences with the virtual. But there's a third issue, that is implementing the NLO splitting functions is not sufficient to get to a next to next link log Parton shower. There is much more to it that we haven't discussed today. If we are talking instead about having an amplitude level shower and that describes collinear singularities correctly, my point of view is that we're still very far away from that. There are many more conceptual issues that we need to understand. Now, in that direction, it could be that having a better gauge, I don't know, might help, but there is much more to explore. So far, you know, people, including you and Simon, have been understanding things in the soft limit, and there's nice literature out there. But when it comes to collinear singularities at the amplitude level, things become more complicated. So there isn't.
So I might just comment.
But what I should mean, what is?
Let
Is
me
there
just.
Is there a concrete algorithm that does an amplitude level shower for the collinear limit out there, is there?
Yes, so this is what we want is what is sometimes called an amplitude level shower. That is to say, it's really the density matrix. So there's a Ket and a Bra state, and you keep track of them separately. And they're both vectors in color and spin space, not just squared, summed over color and spin
I
space.
agree that one
And
can write
that's
down a
what you want.
formalism. I completely agree that one can write down a formalism that is very neat and correct in equations. But writing a
Everything that's so so the coordinate is not an issue at all.
That's for a,
exactly. It's no, I'm aware. That's what I'm saying. There is much more to be understood in that direction. Yeah. So yeah, in more traditional showers, that's been an issue because
The amplitude part just as gauge.
it's the same there. Yeah, exactly. Yeah, exactly. Unless you want to have certain scaling properties of want to organize your singularities in a specific way. I don't know, but without a concrete algorithm, it's difficult to see where the advantage is.
It looks to me we have an excellent topic for discussion, where people here, experts come together and maybe at the next coffee break or so, after the next coffee break, and just hash it out. Okay, so if there are no other questions, let's thank Dave again. Thank you very much.